Alright, welcome back, guys. So we had finished up 6B, in which we were talking about, we were looking at, the part 2 video, we were focusing on finding the standard deviation of a data set. I showed you how to do that using your calculator or a calculator app, and then also I showed you how you could find that using Excel. And we also talked about that range rule of thumb. If you remember, that can be used to give us just an estimate of what the standard deviation might be. And if you recall, the estimate is going to be more accurate the more symmetric shaped the distribution is. Okay, and so in this last section, 6C of Chapter 6, we're going to focus on a specific type of distribution. And this is called the normal distribution, guys. So we've seen it before. It's that symmetric distribution, okay? Or more specifically, it's that bell-shaped symmetric distribution, that distribution that had, one peak, and then it had symmetric tapering tails. We looked at some other distributions like left skewed or right skewed, left tailed, right tailed, or other names for them. But we're just going to kind of zero in on this particular distribution, the normal distribution, talk about some of its properties. Let's see here. Yeah, one thing, if you recall, the peak of the normal distribution corresponds to both the mean, the median, and the mode of the actual distribution. Okay, and this is a very common distribution. In fact, a lot of data sets will exhibit this shape or have this particular distribution. Okay, typically it's like data sets in which the data is coming from things that, so like human height, human weight, the circumference of trees in a forest, or the heights of trees in a forest, things that have many, that involve many factors, okay? Alright, and so let's look at this example 1. So what we have here are two different distributions. Okay, now remember, these shapes that I'm talking about, when I draw them with like a smooth curve, they are just coming from histograms. Okay, if you draw a smooth line that outlines the bars of a histogram, then you get these shapes. All right, so let's look at this A here, this distribution. This is from a famous data set of the chest sizes of close to 6,000 Scottish militiamen. Okay, so basically what they did was they would measure the circumference of the chest of all of these militiamen. Okay, and this is a fairly large data set, right? Close to 6,000, and this was collected way back in 1846. And if you were to make a histogram, or let's say you made a frequency table with that data, and then you made a histogram, this is what it would look like. Okay, and so what we have on the horizontal axis here is the actual chest circumference, and then what we have on the vertical axis is the frequency. Okay, so standard histogram here. And what you can see is that the center, the majority of the data kind of lies right here in this range, anywhere from 38 all the way over here to maybe 42 or 43, okay, and this would be in inches. So you could say that most of these Scottish militiamen had chest sizes that ranged anywhere from 37 to maybe 43 inches in circumference, okay. However, there were also, smaller in stature militiamen that had, smaller chest circumferences. So over here, like 33, 34, 35. And then on the other side, values that are just as rare. Okay, so larger statue militiamen that had chest circumferences of, 44, 45, 46, 48, and then, you know, even way out here, 47, 48, maybe even 49. But these would be very rare, okay? Just like on the other side, these smaller circumferences, these are similarly just as rare. But if you draw kind of a smooth curve around these bars, then this has that, well, I'm not drawing it super well, but it has that symmetric shape, okay? And this is referred to as the normal distribution, or a bell curve, because it looks like a bell. And then B shows the distribution of the population densities of the 50 states, okay? So population density, this is typically like the number of people on average per area, okay? So usually it's measured in like square miles, but it doesn't have to be square miles. It can be some other unit of area, okay? But look here at this distribution. This one, okay, so basically you had the data, which was the population densities. So these were numbers like 400 per whatever the unit of area is, or 600 or 500 or, you know, whatever. And so you came up with a frequency table and you made your histogram, and this is what it looked like. So this is definitely not normal, okay? This data set is not normally distributed. That's the way we would say it. In other words, when you make your histogram, it doesn't look like this symmetric bell curve, does it? In fact, guys, to me it looks more like a right-tailed or right-skewed distribution. See that? Okay. Now, as far as either of these being a normal distribution, well, A is, okay. And then B, I would say, is a right-skewed, or we also refer to it as a right-tailed distribution. Now let's talk about this one just for a minute. So these higher values, or these higher population densities, these probably would correspond to the states that are the most densely populated. So think about like Massachusetts or New Jersey, some of the states on the eastern seaboard. They're very small states, but they have very large numbers of people in them, okay, because they have a lot of really big cities like Boston, for example. Even New York, even though New York's not necessarily a really small state, it has a lot of people in it. Now, the majority of those people probably live in New York City, Manhattan. But anyway, what about the states over here that correspond to these bars? You can see there's a lot of them. These would probably be the western states, states like Wyoming, Montana. They're very large states, and there's very few people. So the population densities are very low. Also, like Alaska, okay? So that's where actually the majority of the states are lying, okay? But anyway, so these are just two examples. All right, let's move on. Okay, which distribution down here appears to be normal? Now, looking at this one, it doesn't really tell us. These are, my guess would be that these are like SAT scores or something like that. This histogram represents SAT scores. Furthermore, you can notice this histogram has a lot of bars. Okay, so it, you know, if you create your frequency table such that you have more and more bins, then you're going to get a histogram with more and more bars, and this will more closely have a contour that's smooth. Okay, the more bars you have, the smoother this is going to appear. So this is definitely normal. Whatever this data is, and doesn't tell us. But let's look at this other distribution here. It does tell us what this one is. Respondents' age at first marriage. Okay, so basically, how old were you when you first got married. And so you can see most of the data is right in here, anywhere from like your late teens to, I don't know, maybe your early to mid 30s. Okay, this is where most of the data is. And then it's rarer to have people in their low teens getting married, and furthermore, it's also rare to have people really past 40 or 45 getting married for the first time. Okay, it does happen, but typically if you haven't been married by the time you're 40 or 45, from a probabilistic standpoint, then you're probably not going to get married. Okay, and so this looks to me like it's also a right skewed distribution. Okay, so different data sets have different distributions, but we're going to focus on data sets that have this normal distribution. Okay, so what types of data would be normally distributed? Okay, well, here's some examples. Adult heights. Okay, I mentioned that earlier. Really, any sort of measurement that has to do with a person's weight, a person's chest circumference, foot size, whatever, height. Okay, tree heights. The heights of red oak trees in a state park, or the trunk circumference or diameter of these red oak trees in a state park. Okay, scores on an SAT test, and that's actually probably what this is right here. IQ scores are actually normally distributed. Okay, interestingly enough. GPAs are probably, grade point averages are probably normally distributed. And then lots of sports statistics. Okay, so these are just a few examples. So conditions for a normal distribution. So typically the data set needs to satisfy these 4 criteria to have that normal shape. Most data values are clustered around the mean, and that would give it a well-defined single peak. Okay, so kind of like right here, or up here when we were talking about the chest sizes of these Scottish militiamen. Furthermore, data values are spread evenly around the mean, and that would create symmetry. So you have, I'm going to refer back to this one, you have just as many values roughly below the mean as you have above. Okay, and the further away you get away from the mean, you have fewer and fewer values. Okay, that's what leads to those tapering tails. Tapering tails on each side. Okay, and then individual data values result from a combination of many different factors. Okay, so such as genetics or environmental factors, things of that nature. Okay. All right, so we're going to look at example 2. We're going to try to determine, would these variables, or would the data in each of these instances, would it be normally distributed, or would it have that normal shape? Okay. All right, so number 1, scores on a very easy test. So I'm going to draw a little graphic for you. Okay. So let's pretend that we had collected scores from this very easy test, and we did our frequency table, and we made a histogram. Okay, so my vertical axis would represent the frequency, and my horizontal axis would represent the scores. Okay, and let's say these were given in percentages. I'm going to go ahead and label this. Okay. Okay, so let's say this is like 10%, 20%, 30%, 40, 50, 60, 70%, 80%, 90%, and then finally the cutoff would be 100, right? You can't get above 100%. And so if it's a very easy test, where are most of the scores going to lie? Well, if it's an easy test, you would expect most of the students to score high on it. Okay, so a histogram might look like this. Most of the scores might be in the A's, and then if it's real easy, you'd still have quite a few B's, but then these lower grades would become increasingly rare, right? There'd hardly be any D's and then hardly any F's. Maybe, there was an odd individual or a couple people that made some low F's, but for the most part, if it's a very easy test, the histogram might look like this. Or in other words, if I were to draw a smooth curve, this would probably be a left skewed distribution, okay? So it's not going to be normal. Now think about number 2, foot lengths of a random sample of adult women, okay? So I can draw a little graphic for this one as well. But you'll have to excuse me because I'm not super familiar with female foot lengths. But nonetheless, if we collected the data, all these different foot sizes, and we made a frequency table, and then we made a little histogram, and our vertical axis would still represent the frequency, and our horizontal axis would represent the foot size. Okay. Now these could be in inches. Let's do that. Let's not do like shoe sizes because that I'm not familiar with. So let's say, I don't know, I guess we'll just do something like this. We'll calibrate this in inches. Okay. So 1 inch, you probably have nobody there, right? Nobody, 2 inches, 3 inches. In fact, you probably wouldn't even start it down here. But let me actually extend this horizontal axis. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. Okay. So I don't know what the average female foot size is, but I might guess it's, I don't know, maybe around 9 or 10 inches. Okay. So that's probably where you would have most of your data, maybe kind of somewhere in here. Okay. And then maybe, there's still quite a few women that have foot sizes anywhere from 10 to 11 inches. But as the sizes get bigger, there's fewer women, okay, with feet that are that long. Okay? And so this kind of falls off. And then the same thing kind of happens on the left-hand side. Okay, there's fewer women that have foot sizes between 7 and 8 inches, and then even fewer, and then maybe just very few rare individuals. Okay, and so what I'm trying to get at is that this would have a normal shape. It would be bell-shaped. And another thing you can know that it would be normally distributed, because what goes into determining the foot length, or really any physical characteristic for that part, or for that matter, is genetics. A lot of genes come into play. Okay, so many genes influence the actual physical size of a female's foot. So anyway, this one would be normally distributed. Okay. All right, let's continue. All right, so now we want to study some properties of this particular distribution. Okay, so we've looked at what types of data would be normally distributed. So if they are normally distributed, what can we then say about the distribution? Okay, a lot of this is going to, well, all of it really is going to hinge on that idea of standard deviation. Okay, so remember, this idea of standard deviation, guys, is a measurement of the variance, okay, or how spread out the data is in a data set. So a higher standard deviation means you're going to have a wider data set, and a lower standard deviation means it's going to be much narrower, okay? Now, when we're talking about these bell curves, that just means you're going to have an either more elongated symmetric bell curve, or you're going to have a more narrower bell curve, where most of the data's just right there in the center. It's not spread out as much. All right, so this next rule right here is really interesting. And this applies to every single normal distribution. Now remember, in the real world, a data set is not going to be perfectly normally distributed, but it's going to be close, okay? And we can approximate a lot of these data sets using this theoretical normal shape. So let's look at this first bullet. It says in a normally distributed data set, about 68% of the data is going to fall within one standard deviation of the mean. Okay, so what do I mean by this? Well, I mean that from one standard deviation above. So let me give you an example. Let's say that the average IQ is 100, and the standard deviation, or the measure of variance in a data set that consists of IQ scores, is maybe 15. Okay, so if the standard deviation is 15 and the mean is 100, then one standard deviation above the mean would be 115. One standard deviation below the mean would be 85. Okay, so what this is telling us right here is that anywhere from 85, one standard deviation below, to one standard deviation above, 115, anywhere from 85 to 115, that's where you're going to have roughly 68% of your IQ scores. Or you can put it another way. You can say 68% of people are going to have IQ scores anywhere from 85 to 115. Okay? And that's what this graphic shows us down here. Now I want to remind you that this little symbol, this Greek letter sigma, this refers to the standard deviation. Okay, but remember, we use sigma to refer to the standard deviation of the population, and we use S to refer to the standard deviation of a sample. So we're talking about this theoretical distribution here, so we're going to be using sigma. So you can see right here in dark green, from one standard deviation below, this negative means one standard deviation below the mean, to one standard deviation above the mean, we've got 68% of our data. Okay? And then look at the second bullet point. About 95% of your data points are going to fall within two standard deviations of the mean. Okay? So look at this. So 2 standard deviations below the mean, down here, all the way up to 2 standard deviations above the mean. You're going to have the majority of the data, okay? 95% of the data set. And then finally, this third bullet point says that 99.7, or almost the entire distribution, will fall within 3 standard deviations of the mean, okay? So if you have a data set that's normally distributed, or roughly normally distributed, whatever that standard deviation of that data set is, if you multiply that by 3, that's going to give you a bound, okay, that will encompass almost your entire data set. And we're going to see this illustrated here below, okay? So guys, you've got to remember this rule. We're going to use it over and over again in this section. It's referred to as the 68, 95, and 99.7 rule for a normal distribution. So just think, 68 refers to the amount of data that you have within one standard deviation. The 95 refers to the percentage of data that you have within 2 standard deviations of the mean. And then even further out, within 3 standard deviations of the mean, you're going to have 99.7, or almost the entire distribution. Okay, so let's put this in context with this example 3. And I think let's see. Yeah, we may stop part 1 with example 3. Let's just see. Okay, it says each test that makes up the SAT. So if you guys don't know, the SAT is a standardized test. It's similar to the ACT in some ways, but also very different. Okay, the ACT tends to try to assess really one's knowledge more than critical thinking ability, and the SAT does a better job at assessing a student's critical thinking ability. So these are typically like college entrance exams. So the SAT, it's designed such that its scores are normally distributed with a mean of 500, okay, and a standard deviation of 100. So what does this mean with respect to the 90, I don't know why I'm saying 90, the 68, 95, 99.7 rule? And then draw a picture. So what I've got is I pasted this graphic in here, okay? And so in the context of this rule, the mean would be right in the middle. So a score of 500 would be right in the middle. That's average. I don't know if any of you guys have taken the ACT. I never did. I took the ACT. The SAT wasn't required for what I needed. Typically the SAT is more required for, you're going to, like, I guess, a more prestigious institution. A lot of private Ivy League institutions are going to require the SAT, but if you're going like here in state to a state school, typically you would only maybe take the SAT if you're applying for graduate school, so if you want to try to earn a master's degree. But anyway, the maximum score is 120, by the way. Or no, is that right? You know what? No, I think it's 1600, the maximum that you can get, if I'm not mistaken. Anyway, so the mean or the average is 500, and the standard. Well, let's just okay. Let's say the mean, and then the standard deviation is 100. Okay. So that means with respect to this rule, the 68% of all scores are going to be within one standard deviation of the mean. Well, if the standard deviation is 100, that means 100 above the mean, which would be 600, to 100 below the mean, which would be 400. Okay? So in other words, 68% of the SAT scores are going to be within this range, from 400 to 600. Okay? And then 95, so I'm just using this rule, okay. 95% of the scores are going to fall within 2 standard deviations of the mean. Well, 2 standard deviations, 2 times 100 is 200. Okay, so 200 above the mean would be 700. And then 200 below the mean would be 300. Okay. So in other words, we could say that 95% of all people that take the SAT are going to score anywhere from 300 to 700. Or you could put it in a probabilistic perspective and say that you have a 95% chance of scoring anywhere from 300 to 700 if you take the SAT. Now, I don't actually know how accurate this information is. I don't know if 500 is actually the mean. And then finally, 3 standard deviations. Well, 3 times 100 is 300, so 300 above the mean would put us way out here at 800. And then 300 below the mean would put us over here at 200. So you could say that 99.7% of the scores are going to fall anywhere from 200 to 800. So basically almost all of the scores. But not quite all of them. There'll still be people that score above 800, and unfortunately there would still be people scoring below 200. Okay. So anyway, what we have done here, guys, you're going to have to do several times, okay, to answer a lot of these questions that we're going to see in the part 2 video. You're going to want to draw your little normal distribution and label it exactly the way I've done, okay, because they're going to be asking us questions related to this normal distribution, okay. Alright, so I think I'm going to stop the part 1 video right there, and then hopefully we'll finish up this section in part 2. Yeah, we definitely should. Okay. Alright, so I'll see you in part 2.